Okay, interpretation of results. What does it mean when we say distance in 10? Okay, so you can take it as 10 units, right? It is more like, so when you're talking about two observations, let's say we are talking about two observations, x1 and x2, right? Two observations, x1 and x2. And there are so many variables, so many features which are scaled, standardized in both, right? So when we am talking about the distance between these two is 10 units, then it means that so you cannot directly say whether it is high or low unless you compare with the others, right? Because it all depends on the number of variables that are there, number of features, and because and the distance method that has been used. For example, whether it's a Euclidean distance or a Manhattan distance, etc. So it is a relative value. So when I'm looking at, let's say, Euclidean distance, probably it's like x1, the variable 1, minus x2 variable 1 squared plus x1 variable 2 minus x2 variable 2 squared plus and so on. So after I did the normalization or after I did the scaling of all the variables, right, it might very well be possible that if even it could be like in the first variable itself, the x1 is like a 2 and x2 is like -1. Then itself you can very well end up with a distance of 10, square root of 9, or probably if this itself is like -3 and if this is like +3. So here itself you could end up with a distance of some 6 units, right? Which is very much possible even after you're doing the normalization process. So sometimes with just two variables or three variables, if I'm getting a distance of 10 units, then it's an indication that the two variables are very, very far off from each other. But if I have 10 variables and I have got the distance as 10 units, then the variables may not be that far off. So, or if I get 50 features and with that 50 variables, I got a distance of 10 units, then the variables are even more closer. So the same distance in absolute sense may not have much of an interpretation as such. I hope that is what you are referring to. But if there is something else, probably you can post your follow-up question as well. Does that answer your question, Shubha? Okay, we have to interpret differently than clustering. Yeah, in clustering, we have a different interpretation. Of course, the distance is the same, but so in clustering, okay, we are going to talk about clustering very soon. But in clustering, wherever the distances are very close, we group them together, right? But here we are not grouping. Here, even though here also we might tend to do a grouping, but we are more interested in identifying those closest variables, closest observations, and pick up the target variable associated with those observations and accordingly assign the target variable to the new test data element. That is what we do in a KNN. KNN, we are actually doing a kind of a prediction, whereas in clustering, we will not do any prediction. We will only do the grouping of the observations. We'll finish off a few more algorithms over the next couple of days, and after that, we will be anyhow moving over to the clustering aspect itself. Okay, can't we start from hyperparameter tuning rather than the first test and then identify hyper? You can very well do when you are actually automating the scenario. You can do, but the reason why we do the first two steps is primarily to look out for if there is any kind of under fitting that is there in the data. So we are just trying to understand what is the level of underfitting that is there. If there is an underfitting, we can scrap the model there itself, right? And the second thing that we do when we test it on the testing data to start with, so the reason why we work with the testing data is if there is any kind of an overfitting. If there is an overfitting, obviously obviously it is very much required to go with a cross validation, right? Otherwise, you can just do a hyper tuning without a cross validation also. So at least to understand if there is an underfitting in the data, it is better to do the initial process. Or sometimes what people also do is once they fit the model, they would also try to understand the parameters of the model. They would try to document the parameters of the model, etc. So which we may not get. Sometimes, so like in some of the models, we would want to get the coefficients of the model for some of the model. So if we want to document those kind of values, then it would be better to run one model rather than a bunch of models, right? So to get some kind of a high level overview of the model, we will initially run it without the hyperparameter tuning. But when you are taking a real world decision, when you are automating the whole process, etc., you may directly go ahead because you may not want to do any intermediate analysis. You may directly want to go ahead with the direct last step, which is that hyperparameter tuning along with the cross validation, everything built into the same. So that is purely for your final, I mean, you have already done enough groundwork. Now you are just automating everything as a part of your model. Now there is no intermediate steps of evaluation and all. You directly want your end-to-end model. Then you build the last step itself directly. So that is generally taken as a part of the automation process, right? But when you are analyzing things in a step-by-step fashion, it's better to do all these things, right? At the time of understanding, etc. But yeah, once you have built everything, you can very well go only with that last step as such. Okay. And yeah. Anyone else in the group? Any other questions? All right, then I'll get started with my today's session. Today's session is about two more techniques. Today, I think we can go with two. One is a decision tree. The second one I'll talk about random forest. So we will take up these two models. the conceptual interpretation of each of these models. And after that, we can go into the implementation aspects of both of them. All right. So decision tree is actually sometimes in the management world also you use this concept of decision tree, which is more like a flow chart. Typically in the management world, when you talk about taking decisions using a decision tree kind of an approach, it is mostly referring to a flow chart kind of a thing. Whereas in this machine learning world or in the statistical world, there is a slight difference with what is called as a decision tree, right? So here also what happens is you start with your entire data, you split the data into different subgroups. You split the data into different subgroups. So you split the data into different subgroups like this. Okay. So you split the data into different subgroups. So this is the kind of a decision tree in the world of statistics. Now, what are some of the important characteristics of this splitting? So what we say is the splitting is done based on some information related metric. So which means this actually falls into the third form of learning that we talked about earlier. We said 4 forms of learning. One is called as error-based learning, where we already talked about 3 major algorithms already, right? One talking about the basic perceptron, one logistic regression, one support vector machine. They are all error-based learning algorithms, right? We are referring to an error metric and we are minimizing that error, etc. Whereas the second kind of learning, which we have already looked at, is a similarity-based learning or a distance-based learning. Sorry, Shubha, I did not get your question. Support vector machine, which we did yesterday. Yesterday was completely about support vector machine. No, I mean, we started late. We started around 7:45 and we went until 9:15 or so, right? Probably you can refer to that video. We did only one model yesterday, which is the support vector machine. Okay. So you can refer to the video, and in case you have some queries on it, you can very well come back. Then similarity or distance-based learning. We have taken up one major algorithm is there, which is a KNN kind of an algorithm. Then the third one that we are picking up today are the information-based learning. So here we talk about information gain. So that is based on some fundamentals coming from information theory. So we talk about information gain. So here we will talk about decision trees, we will talk about random forests, we will talk about gradient boosting and a few other such kind of models. Then the fourth one is typically probabilistic learning, where we would be looking at what is called as a naive-based mechanism. So these are some of the algorithms. Of course, here also we would be looking at a very brief introduction into the artificial neural networks as well. And we have for all the, after we are done with these machine learning aspects, as a part of this course, we are going to talk about a few more advanced aspects as well. But all of them, they are each in one class. So probably we would be talking about time series analysis in 1 to 2 classes. But of course, each one has a potential for 20 classes, but we are just introducing them, right? And probably we don't know in future, we might want to come out with separate classes for each one of them. So then similarly, deep learning. So here the Python usage would be much lesser, right? In all these things, or I would be talking about some of the libraries which can help you, or a quick example which can run through some of the aspects. But we'll have one class or at the max two classes for each of these areas. One is time series analysis, one is deep learning. The third one comes as natural language processing, which is more like a text related analysis. And we'll have one class on image related analysis. So these are all just giving you an introduction, right? Probably there is something on web scraping. All are one session, though you can very well go deeper in each one of them as a separate course in themselves. We would be having just one session, but yeah, that would be after we complete all these machine learning models and for prediction and also for clustering also. So we would be completing the machine learning aspect, and then we would be going to all these in one to two classes. So obviously the depth would not be much higher in these, right? But definitely wanted to give you some kind of insights into each one of them. Yeah, so coming back, there is an information-based learning. So basically, now which means there should be some kind of definition of information. Then only we are talking about an information-based learning. So how do I measure this information? Right? There should be some kind of a measure for this information, because the entire work of decision trees, it relies on the ability to split the data. So we are saying we will split the data based on the information. So what is that measure of information? It is more about the ability. So the good model will come when it is able to split the data based on the information that is obtained by using the various features, right? We are talking about the splits happen based on features. Let's say the split is like age greater than 40 and age less than or equal to 40. Right? The split is happening based on age greater than 40 and age less than or equal to 40. Then the next split might happen based on, let's say, salary greater than 10,000, salary less than or equal to 10. Now, on what basis these nodes are coming, these splits are happening? That is what will become the most important aspect, right? So basically here we have to bring in this concept of information, which actually comes from information theory. And there has to be some kind of a measure for this information. So how much is the improvement in the information? How much is the gain in the information? Improvement, gain. So these are some of the important words that we have to try to understand. Now, as a language, if I want to see here, this is called as the root node. These are all the branch nodes. The last ones are rounds are typically called as leaf nodes. And the ones which are actually the lines out here, they are the rule splits. The rules that are typically used for splitting the node. Right? The rules are typically used for splitting the node. So these are some of the things that so we can be very well aware of. And in another context, so basically for this node, if I take this node is called as the parent node. And for this node, these two are called as the child nodes. So these are some of the terminologies that we may have to be clear with, right? Then here we will have, there are different kinds of algorithms that are available for decision trees, right? So there are different kinds of algorithms because here in the decision trees, we would finally end up with a set of rules, right? So the set of rules will actually guide me. The rules for splitting and the rules for taking a decision. Correct? So here, there are various things that we would be talking about. How do I bring in the concept of cross-validation? Right? The cross-validation can very well be used to decide what should be the... So there are some hyperparameters which we are going to talk about. So based on that hyperparameters, which set of hyperparameters would be more and more suitable can be decided through a kind of a cross-validation exercise. Then how long or how deep should this tree be growing? Should I grow the tree till 10 layers deep or only 2 layers deep? So that is what we talk about, something as pruning. So what is the optimal depth of that particular tree? Where should I stop growing this tree? Or can there be some kind of parallel splits also in the tree? Surrogate splits, right? Can there be some other kind of splits that can come out? Then we can also talk about what are the... So the good thing here is we will also be talking about the variable importance, right? Which variable is more important in predicting the dependent variable or the target variable. So we'll talk about that dimension also. So these are some of the things which can actually run in the form of hyperparameters also, which can really help us in taking some kind of decision. Okay. So now we will talk about the measure. We will talk about the measure for information. So we will talk about two different measures. One is we call as the Gini impurity measure. 。  . 。  . 。 . 。 . 。 . . . 。 . . . 。 . . . 。 . . 。 。 . 。 。 . . 。 . 。 。 . 。 。 。 . 。 。 。 。 。 。 。 . 。 。 . 。 . 。 and the other one is called as entropy, Shannon's entropy, and something called information gain. Right, we'll see with a small example. I'll take it up. Just like the way I took it up in the yesterday's case and in the previous classes also, very small toy examples which can actually help us because the actual calculations happen on a large scale. So first I'll spend some time on this Gini impurity, right? How pure is the information, or how much impure is my information in a data set. How pure is the information or how impure is the information in a data set. So I can very well, so probably let me take a small example and based on that, so we will look at. So let's say I have my gender. I'll take a very simple case, gender. So probably I'll take a few examples randomly. Male, male, female, 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 male. I just took some random data and I'm taking, let's say, default. So default is my target variable and I want to know what is the impurity associated with what is the impurity that is associated with this model. So basically for default, I can also put yes, yes, no, no, yes, because I want to bring in some impurity. No, no. Let's say this is what is the data that I have. So what are we saying here? So how do I measure this impurity? Better look at your target variable and you see, so probably if I look at all males, just do a subset of the data. Subsets. So one subset is males, another subset is females, right? And the way you compute the Gini impurity is across all the subsets, across all the classes, right? You have a class of default versus the no default. Or you have the class of the data wise, you have the classes of males and females here. So you look at for all the various classes that you get, the probability of belonging to that particular class. So here the class you are referring to yes and no, multiplied by 1 minus the probability of differing, not belonging to that particular class. So what we are talking of here, you look at the male and you look at the female, right? First of all, you look at for the entire data. So if I don't do any kind of a splitting on gender, if I don't do any kind of a splitting on the gender, look at in the totality, what is the impurity in the totality? In the totality, the probability of yes is 3/7. The probability of no is 4/7. Right? So if I'm looking at in totality, the impurity is 3/7 into 4/7. P of that class multiplied by 1 minus the probability of that particular class. So for yes, it is 3/7 into 4/7. For no, it is is 4 by 7 into 3 by. Basically, what you will get is you will get it exactly the same because there are only two groups. But doesn't matter if you take only one or you take both also. So it's just a kind of a double thing that can come up. So you can very well say that the impurity right now is either 12 by 49 or 24 by 49. If I go with a very strict calculation, it is 24 by 49 because for all the groups, I will compute what is the probability of that class multiplied by, especially if you have the multi-categories, you will have a difference here. But if you have only two categories, it just is a kind of a double to that of the other, right? So this is what is the impurity. Generally, we say that the impurity is high. So what is the highest value of the impurity? If you really look at both of them being 50-50, right? If the S is 3 by 6 times 3 by 6 plus 3 by 6 or 1 by 2 times 1 by 2. So when both are exactly equal, that is when we will see that our entropy will, that our impurity will be the highest. So when you find the impurity to be around 0.5, that's where you say that the impurity is the highest in the data. But on the other end, if you find that the probability of S is 0 and probability of Y is 1. So what will happen? The probability of S into 1 minus probability of S plus probability of Y no into 1 minus probability of no. So probability of S is 0 times 1 minus probability of S is 1 plus probability of no is 1 into 1 minus probability of no is 0. Overall it is 0. So when the impurity becomes 0, that is when we say that the split or the classification is a very pure. My model is able to differentiate the defaulters and non-defaulters perfectly. But when the impurity is increasing, and it goes up to 0.5, we are seeing that the impurity is very high. Now, coming back to this example, right, we are having 24 by 49 as the impurity, which is almost close to 0.5. So right now, if I don't do any kind of a splitting, it looks like my impurity is around 0.49 or 24 by 49, which is almost equal to 50%. But assuming if I am doing a kind of a split, so in this case, we say data is very impure. Data is very impure. So probably if I just leave it to the randomness, then it is like 3 by 7 and 4 by 7. Allotments to true and false or yes and no. So it is becoming more and more impure. But when I'm able to take that Gini score to 0, so here the Gini score is 24 by 49. When I take the Gini score close to 0, that is when I say I was able to resolve or clean up this impurity. Right? So the Gini coefficient, so that is what will actually, the Gini impurity will actually help me to decide, right? So simply put, now let's say, or probably I should have brought in one more variable also for more clarity. One more is I'll simply bring in a age variable, right? Old and young. I will not use more than that. I'll simply use 4 old and 3 young. Okay, so I'm just using one more. So let's say now I do a subset on splitting. I do a subset on males. Now just look at the males data. There are only 3 males in the data. So out of that, 2 are yes and 1 are no. 2 are yes, 1 are no in the males. Whereas in females, 3 are no and 1 is yes. 1 yes, 3 no. So if I go with the Gini computation, Gini impurity computation, you will be knowing here. This is nothing but 2 by 3 times 1 by 3. This is for this category. Plus 1 by 3 times 2 by 3. So this is becoming 4 by 9. This is becoming 4 by 9. Whereas in this case, it is like 1 by 4 into 3 by 4 plus 3 by 4 into 1 by 4. I hope you are all getting it. So this is becoming 3 by 16 and 3 by 16, 6 by 16. Then what we will say is, we will look at what is the proportion of the males and what is the proportion of females. So the proportion of the males is 3 by 7. And the proportion of females is 4 by 7. So if I go with the calculation, this becomes 4 by 21 plus 3 by 40. So overall also, if I add up, so I may be wrong in my calculation, but I'm able to get a value of 17 by 42. So from 24 by 49, by doing the split based on gender, I was able to reduce. Definitely, it's a reduction, right? We can see if which of these two is greater. I'm sure this one is greater because this is very close to 50%. It is slightly lower than 50%. So I am able to reduce the impurity by this much extent by doing a classification based on gender. Now, just for the sake of example, we will do the distribution based on age. So age wise, we have old and young, right? So there are 4 people here. There are 3 people here. Now, out of these 4, 2 and 2. 2 default, 2 no default. Whereas out of the young, 1 is default, 2 is not default. So if I really do the same exercise here, probability is 2 by 4 into 2 by 4 plus 2 by 4 into 2 by 4. So making it like 1 by 2 into 1 by 2, 1 by 4, 1 by 4 plus 1 by 4, which is becoming 1 by 2. So this is where the maximum, this thing is there. Now here I can very well make it as 1 by 3 into 2 by 3 plus 2 by 3 into 1 by 3. Making it 2 by 9 plus 2 by 9, 4 by 9. Now this one is multiplied by, the weightage is 4 by 7. Oldies are 4 by 7. Here we are multiplying it by 3 by 7. So overall it is becoming like 2 by 7 plus 4 by 21. So this is actually becoming 10 by 21. I don't know whether it got reduced much or not at all. Right? Probably if we see, if I try to find out the difference between these two, right? So or probably it is as good as 20 by 42. If I just do a double, so this is like 20 by 42. So which means the impurity when I am doing a split based on the age, the impurity came down from 24 by 49 to 20 by 42. Whereas when I am doing a splitting based on the gender, it is coming to 17 by 42. So the impurity got reduced more when I am doing a splitting based on the gender, right? When I'm doing a splitting based on the gender, the impurity got reduced more. So which means I would prefer first splitting the data based on the gender. And after that, on the subsets of the data that are formed, if required, I'll do the same exercise. And then if required, I'll split on the age. I'll first split on the gender because the impurity has come down by a large extent. So this is what is the mechanism of using the Gini impurity to reduce or to identify which variable is the most prominent variable to do the splitting. Of course, here in both the variables, I have taken a simple categorical variable with two categories. But I would also extend, right? I mean, the same exercise can be done with more number of categories or even with the numerical variables also. I will talk about those two examples also right now, right? If there are multiple categories, row under subset. Okay, if there is a wrong in my calculation, just excuse me. Right. So where are we referring to, Paras? I might have made a mistake in my calculation. So which aspect are you referring to? I'm really sorry, I did not look at your question immediately. Third row under subset here. 3 by 7 into 4 by 9 plus 4 by 7. Okay, if there is a mistake, probably as long as you have understood the concept, that should be fine. Probably I might make some mistake in the calculation, right? So you can correct it, right? Because when we are doing it in a hurry out here, sometimes some basic, but yeah, if that mistake is actually creating a problem in your understanding of the topic, then probably definitely I will look into it. But if the topic is going fine, I think we can take it up. Now, similarly, what will happen, right? So this is one way which is called Gini impurity. But yeah, I'll finish off the Gini impurity itself. If there are multi-categories, right, probably we talk about default. Let's say I take some default. And probably we talk about a categorical, multi-categorical kind of a categorical variable will take, right? Probably economic status, right? So poor, or we'll say middle class, then rich. Poor, let's say we talk about middle class. So let's say three categories are there here. What if there is a further split now? So now you are splitting the data based on first. So what will happen now? Okay, let me finish this. I'll come to that question. So this is for the first split. Okay. So we have the whole data and this is what we have. So now what generally happens is the same exercise you will perform for all combinations. So just for poor versus not poor. Middle class versus not middle class. Rich versus not rich. Not rich. Then you will also say poor and middle class versus not poor and middle class. So like this, what will happen is, if there are more categories, this is what is an exercise that would be performed. Right? Probably if I look at the initial Gini, initial Gini is 2 by 5 into 3 by 5 plus 3 by 5 into 2 by 5. So the initial Gini is 6 by 25 plus 6 by 25, which is 12 by 25. That's the initial Gini. Right? I can go with poor plus rich, not poor plus rich. Then we talk about middle class plus rich, not middle class plus rich. And probably you can very well talk about all of them combined, which is not a kind of a possibility at all. Okay. So this is as simple as your 12 by 25 itself. This is as simple as 12 by 25 itself. So this would not make any sense. But if I look at first group, poor and not poor. So in the poor group, we have one yes and one no. And in the non-poor group, we have one yes and two no's. So probably here it is 1 by 2 into 1 by 2, right? 1 by 2 into 1 by 2. So yeah, in the poor group, we have 1 by 2 into 1 by 2. In the non-poor group, we have 1 by 3 into, sorry. So this one in the poor group, it will become 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2. So which would be I hope now you have got it. So this is 1 by 2. And in the non-poor group, we'll get 1 by 3 into 2 by 3 plus 2 by 3 into 1 by 3, which is 4 by 9. Weightage wise, this would, poors are only 2. So 2 by 5 into 1 by 2. And the non-poors are 3. So 3 by 5 into 4 by 9. So this would be like 1 by 5 plus 4 by 15. So overall it would come out to 7 by 15. This classification will come to 7 by 15. The impurity with respect to this classification is 7 by 15. Similarly, I can look at middle class versus the non-middle class. In middle class, we have again 1, 1. Whereas in the non-middle class, we have 2. Non-middle class, we have 2. So 1 and 2. So which would exactly be the same, 7 by 15. Then rich versus non-rich. Rich is actually having 0 yeses and 1 no's. And non-rich is actually having 2 yes and 2 no. So again, if I go with that, 0 times 1 plus 1, so 1 times 0. So this part is very pure. Whereas the second part will be like 1 by 2 times 1 by 2 plus 1 by 2 times 1 by 2. So this is the overall coming out to 1 by 2. Weightage wise, this is 1 by 5 times and this is 4 by 5 times. 4 by 5 times 1 by 2, which will come out to 2 by 5. So it might very well be possible. I should compare all these things. And it might very well be possible. Let's say this one is reducing my impurity by a large extent. So if this one reduces the impurity by a large extent, then you might very well say that the rich. So basically what you will do, you will say, I would divide this entire data based on so economic status equal to rich and economic status not equal to rich. So you will get out of this data gets split into something here, the remaining here. Now again on this data, you will redo the whole process. You will redo the whole process on this data. You will redo the whole process on this data until you know what is the impurity now for here. So in the next step, if your impurity is still getting reduced, you will still do the split. But if your impurity is not getting reduced, you will stop your work there itself. Or you will put some kind of a threshold. If the impurity is not reducing beyond this, because sometimes the impurity might reduce just by this much. I don't want that split because it is complicating my rules just for getting that extra reduction in the impurity. So we will put a kind of a threshold that the fall in the impurity should be at least this much. So there are some such kind of things that we will be discussing. But yes, that is one way. So you will continue doing the split on each of the sub branches. On each of the branches, you will be doing this split again and again until your impurities are completely reduced to a significant extent. I hope you are getting that dimension. Okay. So which means I have handled if the variable is having, if my feature variables are binary variables, we have handled it. If they are multi-class variables, we have handled it. So the other possibility is they are numerical variables, right? So probably it's as good as saying age. I'll take it instead of older and younger. So probably I'll say 20, 50, 40, 30, 40, 60, some kind of numbers I'll take. And again here I will take whether, okay, the default. So yes, no, no. Some such kind of value. So we have numerical values here. So what we generally do when there are numerical values is first sort this data on the variable. So what will happen? Age and default. So we'll sort this data. So age 20, yes. Age 30, yes. Age 40, no. Age 50, no. Here it is looking very straightforward. Age 60, no. So what we generally do is, after everything, we put a cut. So we may say less 25. Let's say between these two, we'll take one value. Generally, the minimum, the middle of these two values. So this is 35. This is 45. For every set, you will do this. So what is that you are doing here? You are discretizing the data. So in the first problem, we are talking about, so the first, just like the way we took multiple categories out here. So here we will say age less than 25 versus age greater than 25. This is my first split. So overall, it is 2 by 5 times 3 by 5 plus 3 by 5 times 2 by 5, which is like a 12 by 25. That is the Gini impurity without the split. Now, if I do the age less than 25 split, there is only one observation here. There are 4 observations here. So in this one observation, 1 yes, 0 no. And here I have 1 yes, 3 no's. So obviously, if I look at the probability, 1 times 1 minus 1, which is 0, plus 0 times 1 minus 0, which is 1. So here the probability is 0. 1 by 4 times 3 by 4 plus 3 by 4 times 1 by 4. So here it is coming out to 3 by 16, 6 by 16, which is 3 by 8. So this 1 by 0 is actually multiplied by 1 by 5 because there is only one observation. Here there are 4 observations, so you will multiply by 4 by 5. So this one is having a 0, whereas this one is having 3 by 10. So overall, your impurity has come down to 3 by 10 if you are doing based on age less than 25. But think of the second one, age less than 35 versus age greater than 35. This is the second workout. Right? There are 2 observations here. There are 3 observations here. Now in this 2 observations, both are yes. So 2 and a 0. Whereas here 0 and a 3. So looks like a perfect split. Right? So basically here 2 by 2 times, so basically you can very well say 2 by 2 into 0 plus 0 times 2 by 2. So basically this one is a 0. Here also this is a 0. So this 0 will be multiplied by 2 by 5. This 0 will be multiplied by 3 by 5. So overall the Gini impurity is coming out to be 0. Similarly, you can do this exercise for 45 and 55 as well. So what you will see that this one is having a big reduction in the Gini impurity. The impurity got reduced quite drastically. So because the impurity got reduced drastically, this one would be the most appropriate split. This one would be the most appropriate split. So we have done this for all 3. I think most of the times you will have one of the 3 different kinds of variables based on which you may have to do the splitting. Which part, Alpana? Could you tell me which part you missed out? Splitting based on the age. So we have ordered the data based on the age. Are we clear? Right, I'll go step by step. We have ordered, we have arranged the data based on the age. Right? So then we have categorized. So between every 2 ages, I am taking a midpoint. Right? So after I arranged this whole table, I have arranged in the ascending order of the age. Once I have arranged it in the ascending order of the age, between every age I am taking a mid value. Between every age that I am taking a midpoint. So my rule that is coming out is age less than 25 versus age greater than 20. So which means I am converting the numerical data into a kind of a categorical data. Right? So the age is less than 25 and the age is greater than 25. So it means my data got split like this. So there is one observation with age less than 25 and there are 4 observations with age greater than 25. Right? So then in the age less than 25, there is only 1 yes and 0 no's. Whereas in the age greater than 25, there is 1 yes and 3 no's. So going with P into 1 minus P for yes, P into 1 minus P for no. So P 1 minus P for yes, P 1 minus P for no. So overall it is coming out to be 0. Here P is 1 by 4, 1 minus P is 3 by 4. So for this group, the P is 3 by 4, 1 minus P is 1 by 4. So this is what I got. And finally, this has to be multiplied by the weighted. So there is in this group, there is only one observation. So which means I'll multiply it by 1 by 5. And here there are 4 observations. So I'll multiply by 4 by 5. Overall, I got an impurity of 3 by 5. So in the next step, what I did, I ignored this group. I went with this group, less than 35 versus more than 35. So there are 2 people in this group. There are 3 people in this group. In these 2 people, both of them are yes. 0 no's. In this group, all 3 are no's. 0 yes. So that comes like a more perfect split. Purity is higher there. So wherever purity is more or wherever the impurity is reduced more, where we say that that should be the criteria that should be used for splitting. So that is typically the values that are associated with Gini impurity. Whereas on the other side, just like a Gini impurity, right? Of course, we have covered this in a large depth, but a same mechanism, we have another mechanism called entropy. Based on that entropy, we talk about the information gain. So probably if I have to redo the same example, right, probably let me look at this example that we have used earlier. FM. So the same example I'll take. I think I have omitted one slide here, but yes, age, gender, and the default. I'll take only a simple case here because now I am hoping that you're all clear. Okay. So if I go with entropy and use a concept called information gain. So what the entropy concept is saying, so if you look at the Gini concept, we simply said probability of that class multiplied by 1 minus probability of that class and sum it across. So here in the entropy, what we say is, right, you look at the probability of that class multiplied by the logarithm of the probability of that class. Logarithm base 2, the probability of that particular class, and you add across. So this is what you typically do when you are going with entropy. For each of the classes, you look at the probability. So basically here, the default entropy, right? So if I am talking about 3 yeses and 4 nos. So you can very well say the probability of this class is 3 by 7 multiplied by log of 3 by 7 to the base 2 plus 4 by 7 into log of 4 by 7 to the base 2. This entire thing you put a kind of a minus. So if I typically have to calculate that, right? Let me see if I have any Excel sheet. Of overfitting. So it's better that when we are using these kind of entropy has come down. Entropy has come down from 0.985 to 0.857. So a reduction in entropy. Entropy also is something, a form of error. So a reduction in the entropy is so after a reduction in the entropy, the reduction in the entropy is typically called as information gain. So we could see that we have gained up to 0.13 or something from 0.98. The entropy has fallen to 0.85. So the information gain is around 0.13. So you will say that the information gain for the gender as a variable is 0.128. Similarly, if I do this based on the age category, right? So possibly here I have old versus young, right? As a quick calculation, now I have two yes and two no here. So which means I know minus of 2 by 4 times log of 2 by 4 comma 2 plus the second category is also is like 2 by 4 times log of 2 by 4 to the base 2. This is for the older. So it is coming out to be 1. And for the young, 1 and 2. So this would be minus of 1 by 2 times log of 1 by 2 to the base 2 plus, sorry, not 1 by 2, 1 by 3. 1 by 3 times log of 1 by 3 to the base 2 plus 2 by 3 times log of 2 by 3 to the base 2. So for y, it is this much. So I can very well take the weighted average. So this one, there are 4 older people, 4 by 7. Plus for this one, there are 3 youngsters. So this is coming out to 0.964. So the information gain is there is a reduction in the entropy by this extent. So the reduction in the entropy is only to this extent. So which means there is a decent, there is not much of a decent reduction in the entropy. So if I have to split the data based on one of the variables, so in the first step, this would be the variable that would be used for splitting the data, right? Because it has improvised my overall it has reduced my overall entropy and it has enhanced the information. So gender has sufficient information. What we say is gender has sufficient information to really bifurcate between the people who default and who do not default, especially with respect to this example. I hope you have got it. So that is what is the total conceptual aspect with respect to decision tree. Right? We can, I think, we can quickly look at the code and we will go back to the random forest. But in the meanwhile, if someone is having any kind of query regarding the same, you can let me know. Okay. So again, if you really look at some of the important things, right? But in the meanwhile, if anyone has questions, you can post them. So we are talking about a decision tree classifier. Now this is one important point you should be clear about. If you don't put any kind of constraints or restrictions on the decision tree, right? If there are no restrictions that are put on the decision tree, you will always see that if you are testing it back on the training data, you will always see that there is a 1 in the accuracy score. This is because it keeps on splitting the tree until you get one element in the leaf node. It keeps on that. The default behavior is it keeps on splitting the tree until you end up with one element in each of the leaf nodes, which means there will be a rule for every observation. It tries to create the trees in such a way that every observation has some big set of rules, all complex rules, which are customized to that observation. So if you test it back on the same data, obviously all those rules will come in and you will always get 100% accuracy. This is one limitation with the decision tree. Especially if you don't stop the tree after a few layers of depth, you will always find that the accuracy on the training data is 1. But when you do the same thing on the testing data, your accuracy will fall very badly. Because, as I told you, the rules are customizedly designed for every observation of your training data. Each observation will have a separate rule. And because of that, if you are testing your model back on the same data, obviously because of so many rules, every observation will be classified correctly only. So because of that, you will always find 100% accuracy. This is one important point, either from the interview's perspective or whatever, right? So if you are not pruning the data, pruning is cutting the data tree after a certain depth. Now this is the source of overfitting. So we have told earlier, right, where the model performs very well on the training data, but it underperforms on the testing data. So whenever it underperforms on the testing data, it is a clear example of overfitting that is present in the model. So you could see when I tested back on the testing data, there is a drastic fall. So when this kind of a fall is there, it's very, very essential that I should go with a cross-validation kind of an exercise itself. So otherwise, I can still skip. That's one of the reasons also. We will do all these things. I think when we have started the class today, our friend Shubham has actually said, why do we need to do all this? Why can't I directly start with hyperparameter tuning? Sometimes as a part of understanding, this kind of things really help. So probably I could see that in a very simple model that we have built, that there is a wide difference between the training data accuracy and the testing data accuracy. So which means in these kind of models, there is a definite presence of overfitting. So it's better that when we are using these kind of models, it is very, very essential that I do a cross-validation. Right? Without cross-validation, some simple hyperparameter tuning will not solve my problem because overfitting is bound to be there. Right? So cross-validation will try to handle the overfitting to a decent extent. And similarly, I could see the other metrics as well. Right? And the other things we are not discussing. Now going back to the parameters. One is the criteria. We talked about Gini, entropy. Log loss also is very largely related to entropy with very minor modification. We have actually looked at the log loss earlier. So that for the classification models, the error base, yi times log yi, so it is basically like log loss function we have used. So we say yi times log yi cap. So here the log is not a log 2 plus 1 minus yi times log 1 minus yi cap. So this yi and yi cap are actually, the yi cap is actually the predicted probability. So we can very well get the predicted probabilities, and we will try to minimize the predicted probability. So this in this way it becomes more of a error based learning. By doing a log loss function, it is no more an information based learning. It is becoming an error based learning. But most commonly, I can very well use one of the first two mechanisms. Both are information based learning, either Gini or entropy. Then I can talk about the second hyperparameter, which is maximum depth. How many layers deep I have to go for the tree? How many layers deep I have to go for the tree? So 2 layers deep, 3 layers deep, 4 layers deep, 5 layers. None means go for infinite. Go for the total. So that is another kind of a hyperparameter that I can control. Then minimum samples that should be there in the data in order to split the data. So in each node, in the branch node or in the root node, wherever the node is there, what should be the minimum number of observations that should be there so that the next splitting can actually be initiated. Otherwise, what can happen? So here also we have put very small numbers, right? But in some cases, the large numbers are put at least 10, 20. Only if there are 10 elements in each group, then only you think of splitting. If there are less than 10 elements, don't do the splitting anymore further. So sometimes to reduce, because everything is a memory and all those things, and what we have observed here is too deeper split means too much of customized kind of rules, which may work well on the training data, but they will have a poor performance on the testing data. So that's the reason too much of depth and too few elements in each node, they all lead to a lot of overfitting in the model. Similarly, minimum samples that should be there in the leaf. So if I'm saying 1, then you go until there could be 1 node in each leaf. But in some other cases, I can talk about 3 and 5. So if there are 5 elements in a particular node, no further split. Less than 5, no further split. So there should be minimum of 5 elements in each node. So otherwise you will not split. You will leave it like that itself. So like this, you can actually play around with your hyperparameters. Again, in this case, I have gone with a randomized search, because if I go with a grid search, then it would be 3 times 5, 15 times 4, 60 times 3. 180 different models will be tested, and out of them, whichever comes out to be the best. So if you have time, if you have computing resources, obviously working with a grid search is always a desired one. But otherwise, you can go with a randomized search. So in this randomized search, the default behavior is it will pick up 10 models only. Right, I did not give for, I have gone with the default itself. If you see here, there is a variable called number of iterations. So there is a parameter called number of iterations. So the default number of iterations is always 10. You see, n iter. there is a parameter called N iteration, which is pointing to 10, right? So when I run this, I could see that if I am going with the accuracy as my metric, it says that minimum samples to split is 3. Minimum samples in the leaf should be 5. Maximum depth is 5. And entropy criteria is entropy. I think all of them have given more or less similar. The only thing is when I'm going with the balanced accuracy, there is a slight difference. The minimum samples in the leaf is 1, right? So if you really want to go with this particular model, you can very well suggest this model. When you are going with a balanced accuracy, you can very well suggest that model and you can take it forward. So based on that, you can verify what is the balanced accuracy of this particular model, right? That would be the associated with the decision tree. If there is anything, any query from anyone regarding this decision tree, we will try to address. Otherwise, I want to give a brief background about the random forest also. It should not take much of a time. So if all of us are comfortable, I can move on to the random forest. But otherwise, if there are few questions, I'll try to handle them now. So random forest, not the implementations, we are not taking much time because you can simply run them. The process is more or less similar, right? So wherever concept part of it needs to be understood, we are spending some time to understand that, because the code is already there with you. You can run the code, you can get the response. The only thing is you will have to practice it on different other data sets so that you get a comfort in terms of working towards a solution. Okay, just a brief on limitations of decision trees. In fact, when I wanted to talk with the random forest, I wanted to talk about that. So I'll talk about it. I think we have around half an hour. So I think we can cover the random forest, because in random forest, there is no calculations that we can show, right? It's only the way it executes that would typically come up. So let me spend that time to move towards the random forest. So random forest as an algorithm is not a separate algorithm. Right? So it is actually called as an ensemble model. So in the world of, or probably it's an English word as well, but in the world of machine learning and all, whenever we say ensemble, it's a collection of models. It's not a single model. It's a group of models. It's a collection of models. So basically here, it uses decision tree. So instead of one decision tree, it uses hundreds of decision trees and makes a collective decision. Decision tree will make a decision based on one tree, whereas random forest will make a decision based on hundreds of trees. So it's like a collective decision making. Instead of one tree, here we talk about multiple trees. And multiple trees is always a forest, right? So that is how the name forest has come. Multiple trees come together to form a forest. And we form this forest using a lot of random things. There is a lot of randomness in growing this forest. We'll discuss about it now. So that is the reason it is called as random forest. So random forest is a subset of ensemble. Ensemble is a set of, it's a group of models. It's a collection of models. So random forest is one kind of, it's not a subset. Random forest is one type of ensemble models. So we can talk about boosting, right? We can talk about, I'm not using the words right now, bagging. We can talk about stacking. So all these kinds of things, they are a collection of some models, collection of one or more models, right? They are also a model, but they don't have an individual formulas or let's say, now we talked about a lot when we talked about decision tree. We talked about how the splitting happens, Gini criteria, Gini impurity, then entropy. We talked about a lot of concepts. Similarly, when we talked about support vector machines, we talked about kernels. So there is a lot of concept that is built into each of these algorithms because they are independent in themselves. Whereas a random forest does not have any such kind of behavior. It is a collection of decision trees. So the word collection actually has a different technical name called ensemble. So I can't say it is a subset of ensemble. Ensemble itself is like a collection. Right here, it's a collection of decision trees. It's an ensemble of decision trees. Am I making sense for us? So ensemble is nothing but it's a group. So we will talk about, these are all ensemble models. These are all ensembles. So it's just, you can call it like, I'll probably just give me some more time, right? In case we are not able to do completely today, we'll take it up in the next class as well until you get the comprehension part of it. Okay. So now you can have your questions also, but typically random forests are called random forests fall into the group of collection of decision trees. So instead of having one tree, we'll talk about hundreds of trees. And instead of decision coming from one decision tree, we will say the decision of default versus non-default will come from hundreds of decision trees. So this collection is also called as ensemble. There are a lot of ensemble models. Probably the next couple of ones that we are going to talk about, they all come from the world of ensemble itself. So they don't have a separate formulas or anything of their own. They don't have the mathematical formulation of their own. They just combine. So basically, instead of saying you alone take a decision, we are all taking a decision collectively. Right? So if you really look at now, just to address why not single decision tree, why I require a collection of decision trees. Now, in a decision tree, what is happening? I will grow only one tree. I will create only one tree. And this tree, I'm using, let's say, a Gini impurity. And based on that Gini impurity, the split criteria is decided. That is what we discussed. The split criteria is decided, let's say, based on Gini impurity or an entropy or something. Because of that, no guarantee that all variables, all features may not be used at all. Only a few features will be used. Whereas there could be a few features which might be very important, but because a feature A is already included, feature B, which is slightly inferior to feature A, but overall a very good decider, might completely get ignored altogether. You're getting my point, right? Let's say there are feature A, B, C, D. Normally, individually, it might be like A, B, C are very, very important in determining whether a person will default or not. But in this decision tree, because I'm going with the Gini impurity or something, let's say initially A got the priority for splitting. Now, once I split the data based on A, probably though B is a very important variable, somewhere because A got included, B got ignored altogether, right? And in some cases, probably the other way. If B and C have been used, here I'm referring to variables. So first B, then C, then probably overall reduction in the impurity would have been much higher. But because initially it split based on A, after that it is not able to split based on B and C. So because of that, what has happened, what has been observed by the people is no guarantee that all the features may be used. So the moment it has split, so it might be possible that A could be one kind of a split, B followed by C could be another kind of a split, right? Which could have given a much better reduction in the entropy or the Gini impurity rather than just splitting based on A and then leaving it up. So what has been suggested is sometimes the best results are not coming out through one single decision tree. And here we will also find that the root node is always the same. Once it has identified A as the best variable, it will always split the data based on A itself. So there is no way it will start with a B and then C, then the C also could be added, which could give a much better result. So that dimension cannot come up at all, which means the root has actually a very big influence in your decision. The root is having a very big influence in the decision. So this is where people have found that a single decision tree is not able to give that kind of a result that is typically expected, right? So you may have to put some such kind of a restriction. So that is where what the random forest is trying to handle. These limitations is what are typically being handled by the random forest. What the random forest has said is, so random forest belongs to, I have earlier talked about three kind of ensemble models, right? So boosting, bagging, and stacking. So the random forest actually belongs to a family called bagging. Random forest belongs to a family called bagging. Bag is nothing but bootstrap and then aggregate. Bootstrap and then aggregate. That is what is called as bagging. Okay, so now what happens here is, it actually, now let's say you have In our data, let's say we have 20 features, 20 columns. Features are nothing but columns. Right? We have 20 features. Now, in random forest, what can very well happen is randomly select m features out of 20. Right? Randomly select m features out of 20. Most of the times what they suggest is you try to go with the square root of n. If I'm talking about n is the number of features. So approximately you go with 4 or 5 in this case if there are 20 features. Or nowadays we are also talking about a typical n. So just be around this range. So we are talking about 6 or 7. So randomly we'll ask the system to select. Yeah, we are talking about features. To start with features. Right? So it happens on both, but right now I'm starting with the features. So out of the 20 features, what we are saying the system to say is, you select some 6 features at random. So obviously in each iteration, so let's say like that, we want to build some 500 trees. In each tree, randomly 6 features will be selected. I'm just giving the word 6. Randomly 6 features will be selected and a tree will be built. Right? Randomly 6 features will be selected and only by considering those 6 features, first tree will be built. Then again in the second iteration, another time random 6 features, a second tree. Like that 500 times, 500 different combinations, different or same, we don't know. It's just a random thing. 6 different observations will be, 6 different features will be picked up and tree will be built. Right? Now, in some cases, now this is where the word bootstrapping comes into picture. Bootstrapping contains random selection of observation. Bootstrapping is nothing but random selection of observations with replacement. Random selection of observations with replacement. So if I am having rows of data 1, 2, 3, 4, 5, 6 up to 1000, then what I will do, I will randomly pick one number from this, let's say 5th number. Replace that number again back into the pool, right? 45th number. Replace it again back, 245. Replace it again back, 925. Replace it again back, 45 may come again. Replace it again back, 925 may come again. So like that, I will take some 1000 observations. This is what is bootstrapping. So I am taking a subset of my existing observations only. I'm taking a subset of my observations with again a kind of a replacement. So now here 2 things are happening. One is randomly selecting the rows. Which is what is happening through a mechanism of bootstrapping. Randomly select the columns, features. So this is primarily to ensure that the same root node need not be there all the time. Because if that if A is not coming up in my random 6, there is no way A will be my first split criteria. So we are giving all possibilities. So that way what can happen is the overall accuracy of people have found that doing these two things randomly and creating a large number of trees and get, so it's as good as saying probably instead of having one expert who will help me, I will take the opinions from people with different background so that the final decision could be a more appropriate kind of a decision, right? So I can very well, so this is one extra thing that happens on the top. And let's say 500 trees, each tree will give a different decision. For the testing data, each tree may give a different decision. So the first tree may say this person will default, the second tree may say this person will not default, go with the majority. So do a kind of a voting, and based on that voting, go with the majority. That is what a random forest classifier talks about. So I don't think there is anything extra, because here what are the hyperparameters that can come out? How many trees do I need to go with? Right? How many trees are required? Or probably I can talk about how many features do I need to take in each iteration? Right? How many features do I need to take in each iteration? Or what is the kind of a bootstrap percentage? So here it's like I'm talking about exactly 100%. So if my data is 1000, in bootstrapping also create a data with 1000. So these would be the typical hyperparameters. While it is logical to understand the impact of random selection of features in the outcome, why it is presumed that random row selection will have impact on iteration. Random row selection. See here, instead of, so okay, random row selection, which is what is the bootstrapping that we are talking of. So here the assumption that we are making is every observation is independent in itself. We are trying to choose. So by doing this bootstrapping, we are saying if the same observation comes multiple times also, the result is robust to that. So in any bootstrapping exercise, what we are simply saying is, if each observation has equal probability of occurrence. So I'm saying I can randomly say if the same observation comes twice, thrice also, the result is nowhere different. Now by doing this, what is coming out is some observations are purposefully omitted from the sample. Some observations are purposefully omitted from the sample, because obviously when there is a replacement that is happening, you can, what is happening here, we are randomly playing around with both the rows and the columns to finally arrive at the decision that, I mean, even if some of these observations come many times, because we are making each observation to be independent. So if some of the observations come randomly also, so all these things, so if the same observation comes multiple times, if some of these observations don't come at all, so it's like giving a kind of an interval, right? We are able to give a kind of an interval, and because of which what is happening is the robustness is getting added to the model. So normally also, wherever you want to find out a confidence interval or something, we will actually come out with a confidence interval concept by doing the bootstrapping itself. Wherever, in many kind of places where closed-ended solutions are not there to arrive at your confidence intervals, etc., this kind of a bootstrapping mechanism is typically employed. Because we are assuming that each variable is each observation is independent. The same observation can come any number of times. It hardly matters. You're getting my point? Okay. So that is what it is. I don't see any other conceptual aspects here. Right? Again, we are running this. Now you could see this. If I am running it on the training data, the accuracy can be very, very high. But when I'm going with the testing data, it's still better, 86%. My decision tree has given only 77%. But when I go with this random forest, I got an 86% accuracy. My balanced accuracy also has improved. Without doing the hyperparameter tuning itself, I got a decent accuracy and all. Now here also I can go with, so most of the tree related hyperparameters will still continue. Right? Whereas the major thing that is coming in here, maximum number of features that I should select. That is something that is more and more specific. As we have said, it's always better to look at root of n or something, or probably n by 3. So in that area, you try to go one lesser, one more, and try to give all possible combinations. Right? And you can also talk about number of trees that you would like to grow, because it's completely random. The higher the number is, the better. I mean, not necessary after a certain point. If you don't have too much of bigger data set, you have this, let's say 15 columns or something like that. Whatever may be the number of trees that you grow, beyond a certain point, the error would not be anything reducing quite drastically. So probably normally we talk about 100, 200 kind of trees, but if you want to go until 500 also and you have the bandwidth and the capacity, you can very well go with the same. Again, we have used the random search kind of a thing. And it so came out that on different criteria, different models came out to be the best ones. Right? So probably depending on what is your objective, you can very well go with that. And based on that, I think because we did not use the grid search, this model came slightly inferior to our original model itself. But yeah, sometimes when you are going with a random search, we may have to compromise a little bit. But again, if I have to run a grid search here, 2 times 4, 8 times 4, 32 times 3, 96 times 3. So almost 300 models would be created, and random forest always takes a lot of time because each time so many trees have to be grown. Right? So normally itself, random forest takes more time. Now, if I say so many such kind of models have to be built, obviously the overall time consumption is too higher. So that is the reason we do not go too much into the random forest. I mean, too much into the grid search, unless we have enough time and all. Otherwise, we would fix upon some kind of a random search, but that would compromise a little bit on the overall quality. So if you want to visualize your decision tree, you can very well go with, you can build your decision tree. And there is actually a package in scikit-learn called, there is a function in the module in scikit-learn called tree, where you can very well get your tree model to be represented, and it can be drawn as well. So the tree model can be drawn. So this is just for a kind of a representation. So you can just practice this part out, right? Yeah, that's it. So we will have to move to the next one, which is the gradient boosting. So we'll talk about some of these boosting. So I'll give a little bit of more clarity of bagging and boosting and stacking, the 3 kind of ensembles, and then I'll initiate the gradient boosting in the next class. How each of these ensemble models are different. These are the 3 types of primary ensemble models that I can think about. So what is the difference between them? How they, what what is the difference between them, etc. I would try to cover in my next class. And then we'll move on to the gradient boosting and the other algorithms as such. Okay, I'll stop this here for today.